Hello everybody and welcome to Nuclear Physics Lesson 2. Now back in Lesson 1 we looked at nuclear notation and we saw that a general form of writing down nuclear notation for a nucleus looked like that, where A was the nucleon number and Z was the proton number. Now, in order to calculate the number of neutrons that are in a particular nucleus, we take the nucleon number, nucleon of course being a collective term for protons and neutrons, and from that we subtract the proton number. We also looked at isotopes, and the definition for isotopes is there on the screen. So isotopes are atoms of an element with the same number of protons but a different number of nucleons. And then thirdly, we looked at the decay equations. Now, I'm not going to remind you of the decay equations right now because we're going to be revising them as we go through today's lesson. So in today's lesson, we're going to be looking at NZ graphs. Now, there's an example of an NZ graph on the screen, and you can see that on the x-axis, we have Z, which is the number of protons, and on the y-axis we have N, which denotes the number of neutrons. Now just be careful here, it is N, the number of neutrons, it is not A, which is the number of nucleons. And remember from last lesson and the last slide that we can calculate N by taking the number of nucleons and subtracting from it the number of protons. Now the first feature that you can see on the NZ graph is this line here that comes at 45 degrees from the origin, and that shows you where the number of neutrons is equal to the number of protons. What we're going to do is we're going to go through each of the decay modes in turn and see what effect that's going to have on our NZ graph. The coloured plots on the NZ graph show you all of the different nuclei that can occur. The first one we're going to look at then is the alpha decay. And just to remind you from last time, for alpha decay we have the general equation AZX goes to A minus 4 Z minus 2y, because it's a different element that's occurring there, plus 4 to alpha. So what's occurring in alpha decay then is, remember that the alpha particle is 2 protons and 2 neutrons. So on an NZ graph, if at any point we have our parent nucleus, when it decays, we're losing 2 protons. Now, if we lose 2 protons, it will drop 2 steps on the y-axis. It's also, though, losing 2 protons and will therefore move to the left 2 steps on the x-axis. Our daughter nucleus will finish there, and that will be A minus 4 Z minus 2y. So the total change is that green arrow there. Now, if we relate that back to the colourful graph that we've got over here, we can see that in yellow for alpha decay, most of the nuclei that will tend to decay by alpha decay are up near the top. They're at the higher end of the proton number and obviously on the higher end of the neutron number. There is a tiny little cluster just down here which will decay by alpha. But in general, alpha decay doesn't really occur until you've got a neutron number of above 82. Now for those, they will all therefore decay diagonally in that direction and therefore will move back down, okay, minus 2 protons and minus 2 neutrons. All of our decays will aim to end up on one of these eventually black dots. The black dots here represent the stable nuclides, in other words, the nuclei that don't decay by any mode whatsoever. Now before we move on to the next slide, I'll just talk briefly about beta plus and beta minus decay. If we take beta minus decay first, we can see that all of the beta minus emitters lie above and to the left of the stable line, whereas all the beta plus emitters lie below and to the right of the stable line. And on the next slide we'll explore that. Firstly then, let's remind ourselves of the decay equations for beta decay. In first beta minus decay, from the nucleon point of view, we have a neutron decaying into a proton plus the beta minus, or plus the electron, plus an anti-electron neutrino. For the beta plus, a proton is decaying into a neutron plus a positron plus an electron neutrino. From the nuclear notation point of view, we have A, Z, X. Now remember that because we're losing a neutron but gaining a proton, our nucleon number stays exactly the same. But the gain of a proton is going to cause our proton number to increase by 1, and that will cause a different element as well. Our beta minus particle, now one thing I omitted to talk about last time, mainly because I don't really like it, but I should really talk about it because it's exactly what the exam board expects you to do. The beta minus particle will have a nucleon number of 0, and that's perfectly right because an electron is not a nucleon. And then at the bottom, just to make the maths work, I'm going to put -1 in brackets. Now, a proton number of -1, of course, makes absolutely no sense whatsoever. We put it in brackets to show that it's what I call a pseudo number. It doesn't really exist, but it's there to make the math side of things work out properly. And obviously we have an anti-electron neutrino, and again the numbers on there technically will be 0 and 0 because a neutrino isn't a nucleon and is therefore nothing to do with our nuclear notation. The same for beta plus. We start with AZX. Remember, we are losing a proton, so our proton number becomes Z minus 1 and therefore a different element. It's still A for the nucleon number because we haven't changed the total number of nucleons. Our beta plus particle, 0 and +1 if we're going to put the numbers on, and then our neutrino, 0 and 0 again for the numbers. So let's have a look at what that does on the NZ graph. If we start in the middle here, we'll just have AZX as our general nucleus. When we decay by beta minus decay, then first thing that's happening is that we're losing a neutron. So we will drop 1 step on the N axis, on the vertical axis. We are gaining a proton though at the same time, so we move 1 step to the right. Our daughter nucleus then ends up in that position there, so that will be our daughter nucleus A, Z plus 1, Y. For a beta plus particle, we are gaining a neutron at the expense and at the loss of a proton. So we have a move 1 step up for the gain of a neutron, and we have 1 step left to denote the loss of the proton. Our total move is in that direction, and that will therefore give us A, Z minus 1, Y for our beta plus. So that's the beta plus, and that one there is the beta minus. So hopefully the graph is starting to make a little bit more sense. Whenever a decay occurs, it will normally move from a particular point on the NZ graph towards, or at least in the general direction of, a stable nuclide. So because for beta minus we are moving down and to the right, the beta minus occurs above and to the left of our stable line to move in that direction there. For the beta plus, we are moving up and to the left, and that's why a lot of the beta plus emitters occur below and to the right of our stable line, because we move in that direction there. So now we've explained beta plus, beta minus and alpha decay. We also know that we're always aiming for the stable nuclei because again they don't emit any type of radiation whatsoever. You'll notice there are three other options on here. Now the fission option we're not going to worry about today because that will be the subject of a lesson further down the line. You'll also notice though that we've got these two here, proton and neutron. Now I will mention them anyway. Proton decay or proton emission is really what we should be terming it, is exactly that. It's the emission of a proton. So if we start with AZX, we are emitting a proton. Now if we think about the numbers, the nuclear notation numbers that will occur on a proton, it is a proton, so it will have 1 at the bottom. It is a nucleon, so it will also have 1 at the top. That therefore means that A minus 1 and Z minus 1 are our new numbers on our daughter nucleus. Z has changed, the proton number has changed, and therefore we've changed elements as well. Now from the NZ graph we are just emitting a proton, and therefore we're moving 1 step to the left on the graph. You can see that in the slightly darker pink, which is in this region down here, is where proton emission occurs. Neutron emitters are normally in this region here, and for neutron emission AZX. So for neutron emission then, a neutron is a nucleon, but of course it isn't a proton, so the numbers are 1 and 0. We are losing 1 nucleon, but because we're only losing a neutron, the proton number remains the same, and therefore the element itself remains the same as well. Because we're only losing a neutron, we are just moving 1 step down on the N on that vertical axis. At this point I just want to focus on the stable nuclei just for a few seconds. You remember the stable nuclei are the ones that are denoted in black on our graph. Now the first thing you can see is that actually there are very few stable nuclei compared to all of the other colours that are on there that are the unstable nuclei. Stable nuclei themselves are quite rare in comparison. One thing we can gain from this graph though is, as you can see as the title of this slide, is the NZ ratio, the ratio of the number of neutrons to the number of protons that occur for the stable nuclei. Down the bottom of the graph for the smaller nuclei, we can see that the black dots are pretty much following or are only just above the N is equal to Z line. For the smaller stable nuclei, the number of neutrons and the number of protons in them are roughly the same. We can see that in some examples of stable nuclei that we already know about. If you remember back to the last lesson, we had a look at carbon 12 and oxygen 16. Both of these particular isotopes of carbon and oxygen respectively are both stable. In fact, for those of you that do chemistry, you'll know that carbon 12 is what makes up most of what we are, makes up anything based in carbon really, and it's a good job that it's stable because life really depends on that. Exactly the same with oxygen 16. You'll notice though that for both of these stable nuclei we have exactly N is equal to Z. In carbon 12 we have 6 neutrons and 6 protons, And in oxygen 16, we have 8 neutrons and 8 protons. So N is equal to Z for both of those stable nuclei. And they are quite near the bottom end of our NZ graph. We can see that once we get to around about this point here, which is around about when Z is equal to 20, and therefore around about when N is equal to 20. Up to there, the stable nuclei pretty much follow the NZ line. However, as we get bigger and bigger nuclei, we start to diverge and end up with far more neutrons than we do protons. By the time we get right up to the top here, we end up with 126 neutrons for only 82 protons. At that point, the NZ ratio has increased to approximately 1.5 neutrons for every 1 proton. Now, the reason behind this is due to the forces that are occurring inside the nucleus. Inside the nucleus, we have protons, which, if you remember back to the electric fields topic in the electric fields module, because they are all positive, there is an overall force of repulsion from the protons. There therefore has to be something to give an inward force, give an attractive force, in order to keep the protons and neutrons from flying apart. That attractive force comes from the strong nuclear force, which acts between neutrons and protons. As we increase the number of protons that are in a particular nucleus, that outward force, that repulsive force, is increasing. Because the strong force acts over a much smaller distance and a much shorter distance, remember it only acts up to around about 3 femtometers, we need to put more and more neutrons in to increase the attractive force between all the nucleons in order to balance and to provide an equilibrium between all the nucleons and that repulsive force in the protons and the attractive force from the strong force from all of the nucleons acting on each other. The final decay that we're going to talk about today is electron capture, and it does exactly what the description describes. So we start with our generic nucleus again, and this time we are going to absorb an electron. Now that electron that is absorbed when we are talking about electron capture is an orbital electron. It will tend to be a low energy electron that is orbiting the nucleus that is absorbed into the nucleus. Now to put the numbers on, we have 0 and -1, so we have exactly the same numbers as beta minus particle. And that will then give us, well, let's think about the nucleon number first. Well, on the top line, remember we've got to try and keep it like a mathematical equation, so a plus 0 will equal a. On the bottom line we've got z and we've got -1, so we end up with a proton number of z -1. Therefore we will have a different element, it will be y. We will also add in an electron neutrino just in order to keep everything conserved and to make sure that we are obeying all of our conservation laws there. Now you may notice that electron capture is very similar, at least from the number, the A and Z point of view, as beta plus decay. If we remind ourselves of beta plus, okay, so +1 and 0 there. So remember for beta plus it is z -1 and a plus the electron neutrino. So you can see that the two equations are very similar. From the nucleus point of view, we end up with exactly the same daughter nucleus from the parent nucleus, and we also get an emission of an electron neutrino as well. The mode is ever so slightly different. Instead of a beta plus particle, a positron being emitted, an electron is captured, an electron is absorbed. But the final product from the nucleus point of view, as you can see, is exactly the same. And therefore, if electron capture occurs, it will have exactly the same effect on an NZ graph as beta plus decay. On to the question for today then. So uranium-238 decays by emitting an alpha particle. Is the daughter nucleus more likely to emit a beta minus or a beta plus particle next? So this is more of a conceptual question, but again, go away, grab a piece of paper, scribble some notes down and see if you can work out as a 50-50 shot what the answer is going to be. So in considering this problem then, let's first write down the decay equation and then take it from there. So we start with uranium-238, 92, and that will decay into an alpha particle. And if we follow the numbers through, we will end up with 2, 3, 4 and 90. Now that is thorium. You don't need to know that. That will always be given to you in an exam question. So don't expect you to know that's thorium, but I do expect you to be able to understand 2, 3, 4 and 90 as the numbers on that. Now the next thing I want to do is to have a look at the NZ ratio for both of these nuclei. For the uranium then, we can see that there are 146 neutrons. And for the thorium, there are 144 neutrons. If we now divide both of those by the proton number to calculate the NZ ratio, for the uranium, once we've rounded, we get an answer of 1.59 for the N to Z ratio. Now actually on the calculator before we round, we're actually going to end up with 1.58695, etc. So we have actually rounded up to get that 1.59. For the thorium, the NZ ratio is exactly 1.6. What we can see then is that the NZ ratio has actually increased as that decay has occurred. And we can see that both values are above that number that we came up with earlier of 1.5 for the stable nuclei right up the top of our stable area. So up in this area here, we've got an NZ ratio of approximately 1.5. What we can see then is that thorium-234 nucleus has quite a high N to Z ratio. It has too many neutrons, or more than enough neutrons, for the number of protons that are in it. It will therefore be more likely that a neutron will decay into a proton. Obviously at that point we can then make sure that everything's conserved and say that it will be an electron, or we could also write that it's a beta minus particle that is more likely therefore to be emitted. So that's it for this lesson then. Really what we looked at today is the graph that's on the screen. We've dissected that and had a look and analysed it in a little bit of detail there. You guys obviously just need to make sure that you understand the different regions that are on there, especially the beta plus, the beta minus and the alpha zones and areas that are on that graph. As I said, proton and neutron emission, I've mentioned it because it is on there, but we don't necessarily need to know about it in that much detail. Obviously the other thing you need to know is about the stable nuclei and the fact that down the bottom of the graph we have roughly a 1-to-1 ratio between neutrons and protons, and that by the time we get up to the top, our N to Z ratio will be approximately 1.5, so roughly 1.5 neutrons for every proton that's in there. So that's it for today's lesson. As usual, if you've got any questions, please let me know.